Swayam Prabha. Digital India. Educated India.
Let's get started. So we have spoken extensively on nonlinear spectroscopy. Remember when we treated light in the context of any kind of, when calculating response functions, we treated light as an electromagnetic wave, and the only place it kind of appears is in the interaction term, interaction Hamiltonian, which is mu dot E, and E there is the electromagnetic field, which is classical. When I say classical, we are not using any quantum mechanics to describe light. We are using classical Maxwell's equations. It's a propagating electromagnetic wave. No quantum mechanics involved, no quantization involved. Now, for a long time, at least material spectroscopy or molecular spectroscopy, where we use light to probe properties of materials, also understand many body physics of materials, has explored this exclusively in this semi-classical treatment, with light as classical, matter as quantum. Now, it works beautifully, and we have seen the power of these nonlinear spectroscopies in kind of extracting very critical parameters, very obscure parameters, but with high precision. And there are more and more advanced experimental methods being developed to be applied to more complicated material systems. There are some more theoretical formalisms also developed to kind of capture this nonlinear response effectively. But we have also seen in some of the previous classes that nonlinear spectroscopies come with some intrinsic barriers, right? One of the barrier, which we have kind of alluded to quite early in this particular course, is the fact that when you have, for example, three-field interaction, we assume that it's only a third-order process driving a nonlinear response, which, especially with the kind of intensities used, we cannot be absolutely sure. There could be higher-order contributions. That is a problem in general. And this leads to some kind of discrepancies, and we have kind of seen such discrepancies. For example, I've shown an example where if I measure homogeneous line width as a function of fluence, the zero intercept, we'll again revisit that one, the zero intercept was not matching the lifetime. It is something else which is kind of dominating. That is one problem. The second problem is, in a sense, related to the bloboscopy. There are still, even with 2D spectroscopy, where we kind of separated a lot of multiple contributions for material systems, there is still some overlapping contributions existing. And these overlapping contributions, like for refacing diagram, you can still write 6 particular Feynman pathways all contributed to refacing. And all of them, depending on the energetics involved, can overlap and can lead to ambiguities in the interpretation of the nonlinear spectral light shape. Okay, so these are important problems. The first problem is where you have a higher order nonlinearities contributing can be reduced, can be eliminated if you reduce the excitation fluence, right? But there is a limit to that. If you have done experimental work, you would have used some form of, especially with light, you would have used some form of detectors, and detectors have intrinsic noise floors, and at the end of the day, you cannot go beyond that. On top of that, lasers have intrinsic instability, so on and so forth. Beyond all of this, if you use classical light, nature itself puts a limit to how much you can, what is the kind of signal to noise ratio one can assess, and that's called standard quantum limit or short noise limit, and that puts kind of a bottleneck on how low you can go with your excitation fluence. Okay, in the first part of this lecture, we'll go through that. We'll go through how we can use or go beyond classical light into quantum light, what we call as quantum light. We'll also define what quantum light is and see if we can gain in sensitivity so that we can go at low fluences. That is part number one. Part number two is again the second problem that we have spoken about, overlapping features, a lot of overlapping features. Now we want to explore, can I use some quantum properties of light, real quantum properties of light, to unambiguously measure some system parameters, okay, where I won't have overlapping contributions. The answer for that as of now is we don't know yet. We are still exploring, so it's kind of a really an emerging field. So which means that we are in a process where we are asking ourselves, can I do this? And if I can do this in a particular way, what is the best way to do a measurement? So it's really at the forefront of emerging research. Okay, so with that intro, let's go into the outline. The outline is we're going to start with, in these lectures you can see there's a PowerPoint presentation. So unlike some of the lectures, there's no handwritten notes, so you can kind of go over the things with an outline. But the reason it's like that is because I removed the mathematical rigor, because there's a lot of math which I'm not putting out, even though it could be relevant. I'm not putting out because it can be a bit advanced. That's a note. Okay. So the outline for this part is we'll start with defining what quantum light is. So I said light is classical or quantum. At a fundamental level, you can ask this fundamental, almost a philosophical question as to what is light, right? What is light? Energy propagating. Okay, let's get a bit more. I mean, it is, but energy can be of any form. What is light? What do you think? How do you want to define light? Electric and magnetic fields, right? Okay. So what is so quantum about this or classical about this? So I want to highlight that light is light. If you ask what is light, light is light. Light is there, and it's how we define it, right? Depending on the kind of observations we are making. That's at the bottom of the philosophy of physics, right? At the end of the day, we're not trying to define reality, but create a framework in order to describe a phenomena. That is at the heart of philosophy of physics, in my opinion, at least. So light is light, whether you treat it as electromagnetic wave or a photon, that depends on what kind of observation you are making. Okay, so in that sense, when I say what is quantum light, that has to be tied inherently to an observation process. Okay, that's when you start thinking about, okay, now there is a need to quantize my light and treat it as a quantum mechanical entity. So we'll talk about that, sort of an intro to quantum mechanical description of light. Again, not a mathematically rigorous intro, but more kind of a descriptive intro. The second part, using this understanding, we'll go into what is quantum advantage in spectroscopy, in optical spectroscopy. So there the point is, I kind of pointed out again the fact that you have a short noise limit. There's a minimum limit that beyond which we cannot measure with reliability. We will define what that short noise limit, it's also sometimes called standard quantum limit, and we will see how using what we call as squeeze light, we can go beyond it. Okay, we are not the only ones, and we are not the first ones to think about this. There is also a spectacular tool called LIGO, which measures gravitational waves, and this uses the squeezing. Okay, but use of squeezing in the context of spectroscopy is rather new, and rather, I would say, in a very nascent stage, very, very fertile field to think about it. Right? And lastly, I will going to end with emerging perspectives. The quantum advantage squeezing is established. You can have textbooks on this already. Okay, but emerging perspectives are something really new where we don't know what we are seeing. Okay, all right. So we already answered this. What is light? Classical picture, electromagnetic wave, quantum picture, photon. Let's talk about electromagnetic waves. So there is an electromagnetic wave in this a pulse going through a sample. The sample generates, or the electric field in the material generates a linear polarization in the first approximation, which emits radiation, which travels in the same direction as your input field, which your detector measures, right? Of course, the polarization can be expanded into higher orders. Let's say we are talking about linear polarization. What we measure at the detector is the intensity of the electromagnetic wave, right? Sometimes, if we are kind of smart enough, like we did with 2D spectroscopy, we can measure the amplitude and phase by interfering the signal with another electric field, or what we call as local oscillator, whose amplitude and phase we know, and then we can gain also access to amplitude and phase. But in general, in a detector, you're going to have, most of the detectors are integrated, time integrated. You will just integrate over the entire signal over into time, square that, right? And we know that that part of the electric field, the linear component, the emitted field of the polarization, has access to what we call as the absorption spectrum. Is everybody happy with the equation right on the slide, which I have highlighted this particular equation? We have spent a lot of time to develop this formalism using correlation. You can kind of write this in the form of what we call as correlation functions, dipole moment correlation functions, dipole operator correlation functions. So that's classical spectroscopy, right? Everybody is comfortable with this. Now, how do you detect electromagnetic wave? What is a detector made of? Especially experimentalists in the group. What is a detector made of? Diode. Avalanche diode is for a single photon detector. Fine. Time integrated detector. You go to Thor Labs and buy a silicon detector, right? At the heart of it, what is happening? Light is absorbed, and then what happens? So at the heart of it is a semiconductor, right? There has to be a semiconductor where there is no conduction in the absence of light. Light goes, it generates electrons in the conduction band. It forms a current. You generate a photovoltage. You can make a diode out of it that's why for more practical purpose. But you're going to generate a voltage, and that happens. What happens in the detector is excitation of electrons in a semiconductor going from valence to conduction band. Right? Everybody is happy with that. Happy with that. But it's not that every time my light is incident on my detector, on the semiconductor, there is a absorption event happening. The fact that you can write a so-called absorption coefficient, right, which means that the absorption is not always 100%, right? Sometimes it happens, sometimes it doesn't happen. That's why, for example, detector has a detection efficiency which is not 100%. It's actually very difficult to make it 100%. Either because absorption is not efficient, or because whatever you generate is collected as a photocurrent or measured as a photovoltage, because there are recombination events happening simultaneously where your signal is lost. So it is not unreasonable to say detection has intrinsic stochasticity in it, intrinsic noise to it, because of whatever processes are happening in the background. You agree with me on that? So if I have to see, the voltage has some small fluctuations. It's not a same voltage, it will go up and down in time. It will not be the same. And this is again something you would have, if you have done any kind of measurement in the lab, you know there is noise. There's noise coming from electronics, from everything else. Okay, cool. Now let's take a case where I reduce the intensity of light. I keep reducing the intensity of light. Keep reducing. When the intensity is reduced, let's say I have some kind of ideal detector. Now what happens is that my light is not coming all the time. There is intrinsic stochasticity. Most of the time, my detector will be off. Once in a while, it will blurt out a voltage pulse. You agree with me on that? So now I'll have some kind of pulses of voltage coming out because I don't have light all the time. When I have low intensity means that I can sometimes the stochasticity of my detector does not see light anymore because there are other events competing with it, obscuring the observation of a photovoltage. Okay, so now in this particular time trace, now I can divide it into time zones of certain time period tau. Okay, and now I say every time I detect or generate a voltage, I attribute it as a single photon detection event. I'm not detecting single photon. I'm only attributing, saying I'm measuring some form of single photon detection event. Okay. So once I have this, there is an events, so I can connect it to a counter. It's like clicks, right? It clicks, and I can connect it to a counter, and from their counter, I can measure a histogram. You're all fine with this? You're all fine with this, right? Now, once I have an histogram, as soon as I have histogram, what comes to our mind? Statistics. It will have a mean and a variance, right? It will have a mean and a variance. Now, for typical classical light, what we define as classical coherent light, the mean will be exactly equal to the variance, because it follows what's called Poisson distribution. And Poisson distribution, it can be shown actually starting with Maxwell's equations. You can show that in Poisson, you can get a Poisson distribution, and they look something like this for some average number, mean number of photons. If mean number of photons is like this, your histogram is going to look like that. If the mean number of photons is 3, you'll have the peak around 3, but then you'll have some kind of distribution around it. Okay. Now this observation of statistics of photon detection enables you to distinguish different forms or different kinds of light. Okay. What are the kinds of light you know already? You don't tell me. You know already too much because you do quantum light. Yeah, you already kind of leaked out. There is thermal light. Look around, right? What are the sources of light? There is, of course, if you go out, there is sun, or there is these LED lights or incandescent bulbs and whatever, right? This where the emission is happening in an incoherent way, randomly, right? There are some processes happening, which some kind of relaxation processes which happen, like in detection, exactly the same way. You can also have emission in a stochastic manner. There is no coherence between different emission events, or their coherence is extremely limited. And this is thermal light. That's something you know. But we also know you can generate lasers by stimulated emission, and that will impose coherence on what you're saying, and that is what is called coherent light. Two forms of light. Now I'm going to introduce the third form of light called quantum light. How I'm going to define this? The classification is purely not based on how it's generated, but on the statistics. So if I have a perfect Poissonian distribution of these numbers, of number of photons that I'm measuring, and the intensity is constant, let's say, then this is referred to coherent light. If I have a super Poissonian distribution, where my variance is much larger than my mean photon number, then it is referred to as thermal light, or partially coherent light will fall. Whatever is around you is super Poissonian. Now there is one form of light where your variance drops substantially. Variance is much smaller than the mean value. Now it so happens this form of sub-Poissonian distribution cannot be explained with classical electromagnetics. We have to use quantized electromagnetic field. I'm not going to show why and how, but this is what we refer to as quantum light. Okay, let's go into a brief tour on the quantum mechanical treatment of light. This is not a rigorous treatment. This is mostly an introduction. So don't question me too much on the math of this. Okay, we all know how to treat light. Everybody knows this. If you're a physics student, you should have this tattooed on your brain, right? It should be really on your head all the time. Okay, so these are the four Maxwell's equations, beautiful Maxwell's equations in its differential form. For light, let's say there is no free charges and free current for a propagating electromagnetic field, then I can condense these and write my wave equation in the form of my vector potential. Right, everybody's happy with that, and it's not an unreasonable thing, a vector potential, to have been composed of a set of plane waves. Right? Agreed? So I can there is an analogy between the vector potential written in terms of that way and a position of some charged particle. There is some kind of correlation. In fact, when you write out the Hamiltonian of your electromagnetic wave, okay, there is some kind, of course, for a bunch of harmonic oscillators, you can define your position and momenta, which can be equated to your electric and magnetic fields. Okay, so one could, it's not impossible to think of electromagnetic waves as behaving as harmonic oscillators. Right? It's not unreasonable. It's actually perfect for electromagnetic wave. There is no defacing for a propagating electromagnetic wave. It's perfect harmonic oscillator. Okay, so this is where we are starting. Okay, classical harmonic oscillator. So let's, for now, we know light can be treated as a harmonic oscillator. So we'll now look at classical harmonic oscillator, whose Hamiltonian is written in terms of the position and momenta, and you can write the equation of motion for calculating the dynamics of this. Okay, whose solutions is going to be oscillatory. And now I can kind of describe the dynamics of my harmonic oscillator in a phase space trajectory with the coordinates given by the position and momenta. Everybody comfortable with that? That's something you would have seen. So basically, your harmonic oscillator is going around, is oscillating. You're basically tracing a circle in the phase space. Right? Is everybody comfortable? So this is classical. Okay. Light also can be described like this, and so I should be able to describe light, propagation of light, similarly in similar phase space trajectory. Okay. Now, what those coordinates are, we'll talk about that in a while. So now let's look at light as a harmonic oscillator. So now we are harmonic oscillator, so we replace our position and momentum with associated operators which do not commute. That's very nice. Now what we define are two new operators, what we call as the quadrature operators, x1 and x2. In a sense, what these operators are doing, these are basically removing the dimensions of your position and momentum. We're kind of making them dimensionless. That's what we are doing. And if you have already done a bit of quantum mechanics, you can see that these are related to ladder operators, which can be actually rigorously shown. It's not complicated. Okay, your A dagger is your creation, A is your annihilation operator. Okay, and if I rewrite my Hamiltonian now in terms of my quadrature operators, it looks something like that, which I can also write in the form of my ladder operators. So that's your Hamiltonian for a quantum harmonic oscillator. Everybody knows this, right? Now it so happens these quadrature operators can be shown, each of them, to be proportional to your electric and magnetic fields, quantum mechanical. Again, not going to show that, but it can be shown. Now this Hamiltonian here is basically infinite Hilbert space with the basis to be the numbered state. Again, this is basic quantum mechanics. Sometimes we also call the number state as a Fock state, where number operator is A dagger A. When it acts on a particular mode n, it generates n number of dot modes. Right? That's a number operator. Okay. Remember, x1 and x2, like position momenta, do not commute, and so it's subjected to Heisenberg uncertainty principle, which means if I have, which I'm looking at uncertainty x1 multiplied by uncertainty x2, it should always be greater than or equal to 1 over 4. That is Heisenberg uncertainty associated with quadrature operators. Okay, now let's go back to phase-space trajectory, thinking about phase-space trajectory for quantum harmonic oscillator. Now what you will do, we have already moved on from the space defined by position and momenta to this dimensionless quadrature operators. We'll replace my P and Q with x1, x2. Everybody is happy with that, right? And for a classical coherent state where there is no quantum mechanics, no Heisenberg uncertainty, there is no correlation between the uncertainty in x1 and x2. In fact, uncertainty x1, uncertainty x2 is 0, which means very deterministic. You know exactly what is the position and momentum of your harmonic oscillator. Agreed? Now, when I think of harmonic oscillator, always keep in mind I'm making analogous connection with light. That's a very important thing. Now, if I have to replace now something of like a point in space with something with uncertainty, now I'll replace that with some kind of circle, right, with certain dimension. So now I can move on to description in a quantum harmonic oscillator, where now my state is described not by a point but by a circle, right, whose dimensions are limited by Heisenberg uncertainty principle. Okay, and this is a representation of a quantum coherent state, and basically the amplitude, which is the radius of this representation here, is related to the amplitude of my electromagnetic field. Amplitude of electromagnetic field in the context of quantum mechanics is simply the number, right, number of photons. It is exactly square root of the mean number of photons here. Okay, and you also have, and that mean number has some uncertainty, as you can see. It has some uncertainty. It's not one singular point, it's not one singular number, but it has certain variance associated with it, because it's not a singular point but rather a distribution. So you'll have a distribution on the number, uncertainty over the number, or a variance over the number. You also have variance over the phase. The phase is given by this angle. My line makes my position vector of that state makes with my x-axis here, and that has also a distribution, right? So already you can kind of see that when I'm thinking of my phase-space representation of quantum harmonic oscillator, where it's no longer a point but rather a distribution, with the size of distribution limited by Heisenberg uncertainty, which means it has minimum of half in this case, it cannot go less than that. This leads to an uncertainty both in the number density of my photon state, or number of the photons in the mode, and also uncertainty in the phase of my electromagnetic field. Great. So for a coherent state, your delta x1 will be exactly equal to delta x2 will be half. So the product is the minimum. Okay. How do I visualize it? How do I visualize this? One way of visualizing this is if I look at evolution of my harmonic oscillator or my light in phase space. This is this circle going around. The way to think about it is when you draw an electromagnetic wave, you draw a nice sinusoidal wave, but it's not going to be a sinusoidal wave. Pardon my horrible artistic skills, that's the best I could do, but I should have used Python to make this. But what usually you draw this, right? You draw this as electromagnetic wave, but then what the uncertainty is telling is that I don't know this for sure. There is some amplitude uncertainty, there is also some phase uncertainty. That is coming because of the quantum description. Okay, which, by the way, when I do photon detection, number distribution, I capture that. I am capturing that. right? When you just do a measurement of intensity, you will lose it because that's not really accessing the quantum mechanical properties of light. Once I go to low enough light density, light fluence, when I start measuring the number of photons within a particular time window and building a histogram about that, then I am accessing a property of light which is not described classically. So classically, classical electromagnetic dynamics will tell you that my variance will be 0. I should be able to measure my intensity absolutely perfectly, deterministically. Once I go into quantum, that's when I realize, oh, I cannot measure the number of photons absolutely deterministically. They'll always have intrinsically some uncertainty built around it. Okay. The same goes with phase. If I go and measure the phase using some interferometry, the phase will have uncertainty. Fine? Questions? Questions? This is what is referred to as the standard quantum limit to the variance. When you do a measurement, even if in the spectacular case where your laser is absolutely stable, your detectors are also perfectly efficient, 100%, whatever, intrinsically your light comes with a variance built into it. Because at a foundational level, light is quantum mechanical or can be treated as quantum mechanical. And because of that, you cannot measure, for example, amplitude or the phase of the electromagnetic field beyond certain limit in the variance. Okay, that is standard quantum limit, sometimes also referred to as the short noise limit. Everybody okay with that definition? Okay, can I overcome this? Now in this context, I said, oh, maybe using quantum light, I can overcome this. Let's take a simple case of a pure Fock state. A pure Fock state is when you know for sure your number very precisely. Number of photons is either 1 or 2 or 3 or so on and so forth. You know exactly that. Now pure Fock state representation in the phase space trajectory is a circle. It's not a point, it's a circle which has a radius given by square root of n. Here, the variance, this is of course an extreme case, it's an extreme case of sub-Poissonian light. The variance is not only less than the mean, it's 0. Okay, but in this case, if you try to use the Fock state to a phase measurement, the phase uncertainty will be infinity. It has to be, because otherwise you are violating Heisenberg uncertainty principle. Okay, so within the quantum mechanical description, it is impossible to measure amplitude and phase of the electromagnetic field exactly. And remember, all our coherent nonlinear response is embedded in the ability to measure amplitude and phase at the end of the day. That's kind of deeply rooted for us into what we want to do. Okay, this is the uncertainty for a Fock state. Let's not worry about that. So how do we do this? Now, if I plot my delta x2 and delta x1 for different kind of representation for different states, it cannot cross this barrier. Right? It cannot cross this barrier, because if it crosses the barrier, then the product will become less than 1/4. Your coherent state is right there. That's your coherent state. Okay. But let's say on this boundary of possibilities, I could potentially go slightly above or below this coherent state point. So that's an eddy photon number state. So one can go, if I remove those parts, so I kind of remove those parts and identify only these points in this representation or kind of space, then you see when I go to somewhere here, I am increasing my uncertainty in the x2 quadrature, but I am reducing the uncertainty on x1 quadrature. So one can increase the precision of one of the quadrature by sacrificing the other. Right? This is basically at the fundamental level what squeezing means, right? Remember your state. The name squeezing comes because if I take a state which is not a point, it's a circle, it's a nice given circle, you basically squeeze it either in the form of amplitude or phase. So it becomes a oval, sort of, is squeezing it, and then you will increase the um, the, the the certainty on one at the expense of the other. Okay, this is quantum mechanically what squeezing operator will look like. And the most important parameter is a squeezing parameter. For different kinds of light which is being produced, squeeze light, you can write associated squeezing parameters. Again, something which I'm not going to do. I'm going to show some examples of squeeze states, but I'm not going to describe how exactly the squeezing comes over, but it's kind of something that you can think about. So now if I take a coherent state, it's going to look like this. A state which has squeezed amplitude will look like this, the phase space representation. As you can see, there is squeezing in this direction, so you're increasing the uh, uh, the certainty in the measurement of the number of the photons, but you have to give up the precision on the phase, or you can also have squeezed phase states. Okay, so this is something I took from Wikipedia literally, and here you can kind of see how in a coherent state the electromagnetic wave is going to look like this. A phase squeeze state will look like this, where there is huge uncertainty in the amplitude of the field, whereas if I have amplitude squeeze state, there's a huge uncertainty in the phase. All right, so this is basically, you can beat, this is evolution of a squeeze state, for example, you could beat uncertainty. Okay, you can beat the standard quantum limit, you can go beyond the short noise limit by doing this. Okay, which is at the heart of this. Now, how do you generate a squeeze state? How do you generate a squeeze state? And I want to show one of the, in my opinion, one of the first demonstrations of squeeze states. It happened quite early, and it uses spontaneous parametric down conversion, which Ritesh is an expert on. You know it very well, right? So you take basically what happens, you come with a photon of very high energy, similar to the optical parametric amplification we have seen in the other class. Come with a photon of high energy. This photon spontaneously down converts in a nonlinear crystal due to a second order nonlinear process to generate a signal Neidler photon. Okay, and this is how it looks. This is a real live image of SPDC. Now, why there are two cones, so on and so forth, it's a topic for a later time. We will not go into that. But it so happens that this SPDC light can be used as squeeze state. It's later on I'll show this is also an entangled state, which is kind of confusing. When does it squeezing happen? When does entanglement happens? So happens the trick lies in the observation. It's not the actual what you're generating here is a maximally entangled photons, but we'll define it later what entanglement means. But it's kind of fascinating to see that the same source can be used also as a squeeze state. What it actually is a two-mode state generated from vacuum. A lot of words there, but that's your squeezing parameter, which is related to the second order nonlinearity, the interaction time, but also the number of photons in the pump. Okay, so it's kind of interesting. Okay, so this is one of the first experiments ever done and ever demonstrated squeezing. Okay, it was done in 1986. Okay, so it is almost 40 years old technology. So basically what it does is that you come with your laser source, an Nd:YAG laser at certain omega. Okay, go through second harmonic, you generate 2 omega. Okay, but you have a beam splitter here, so you take part of the beam out here. So let's keep that there. So this beam goes, generates second harmonic, and it goes through an SPDC process which degenerate down converted photons. Signal idler will have the same frequency, which means that if I'm coming with 2 omega, my 2 photons will be omega each. But this SPDC is type 2. It's type 2, so they will have opposite polarizations. We have discussed type 1 and type 2 crystals in the previous class. So you will see that in this case, these two will be oppositely polarized. Okay, fine. So two oppositely polarized. They're co-propagating. We are not separating the 2 photons. Very important point. We are not separating 2 photons. We have this beam here, which is coming from the laser, which we have not dumped, which is exactly at omega. Taking the omega. We are adding some phase delay to it, put it on a translation stage, or like yesterday we have discussed how we can use a spatial light modulator to delay the pulses. So it's a phase delay, and getting it and letting it interfere with our SPDC mode. Okay, there are SPDC mode here interferes with this. Now it so happens that because of the polarization being orthogonal, only one of the photons will effectively interfere with this mode. This is what we call as the local oscillator, and this is what is called homodyne detection. So here it will interfere, and then we detect at N1 and N2, and then we estimate this difference. Okay, this difference between N1 and N2. And what is plotted here is the variance of this signal, variance of this delta n square, which is kind of related to the interference effect, as a function of theta. Now it can be shown, the short noise limit, the standard quantum limit, it's an exercise I wanted to go and think about, for coherent light is when this variance is exactly 1. Because I have a quantum light here interfering with my local oscillator, which by the way is a coherent source, but this is the quantum light, you will see that this variance goes less than 1. And in this region of space, this region of thetas, you are beating the short noise limit. You are going beyond what is possible with classical light, which if you have done the same experiment, instead of having SPDC photons, remove this whole thing, take this omega there and did the same experiment, this whole thing would have shifted up, and you're limited by 1. It will be absolute limit, and that can be shown mathematically, because for coherent light, variance will be exactly equal to mean number, and you put that in there and you calculate the variance, and you can show this. Okay, so this is one of the first demonstrations, okay, of going beyond the short noise limit. A caveat here, an important caveat, is that I said it, I already kind of alluded to the fact that SPDC light is also an entangled state. The signal and idler modes cannot be separated out as 2 independent modes, they are interrelated. Okay, again, this is a bit of detail which probably is going beyond the scope of this particular class, but I want to kind of put it out. What you're actually doing here is that you're tracing out only one of the modes. So you're kind of generating what's called a mixed state, which is akin to a thermal state, but in this case that is squeezed. So mathematically you should be able to show this, that this is, so basically I generate an entangled state, but by disregarding one of the photons, you're using only one of the photons and you're kind of disregarding the other photon, you're doing a partial trace of your density matrix, and that, because of the nature of the SPDC photon itself, allows you to access the squeezing parameter, okay, which is a very important thing. Okay, once you start detecting both, then you are tracing out the entire density matrix, then it's no longer mixed, then you will not be able to do a squeezing operation on SPDC. So that's a note that I'm not going to discuss that, but it's something that to keep in mind. If you're interested, more than happy to discuss that in greater detail. All right, so these are different representations of what quantum advantage will look like. It's uncertainty in phase. For example, this is the standard quantum limit. As you increase number of photons, it can be shown that the standard quantum limit goes as 1 over square root of n. If I have correlated photons, if I just have two photons which are correlated and you're kind of doing a balance detection by kind of ensuring that you're accounting for fluctuations in one by taking another correlated photon in another, like in entangled photon regime, you go to what's called Heisenberg limit, which is scales as 1 over square root n. Beyond that, if you access squeeze state, you go into a very new regime limited by what's called Kramer-Rauf bound, which again it can be described mathematically, which I'm not going to do. So the idea is, usually when I do spectroscopy, you are right here. You're limited by the standard quantum limit. You are not going to go beat that. We want to be able to beat that. To be able to beat that, we should effectively bring in squeeze states in spectroscopy as probes, right? And guess what? One of the first measurements of that kind, at least in my knowledge, in my limited knowledge, has been done and published only in 2021. This, I would say, is a seminal paper. It's quantum enhanced Raman spectroscopy, where they use squeeze states, specifically amplitude squeeze states. Not going into too much description, but in this case, guess what they use to generate amplitude squeeze states? They use optical parametric amplifier, OPA, that you have in your lab that we discuss extensively. And OPA can be shown that it can produce amplitude squeeze states. Not SPDC, OPA, okay? And in OPA, unlike SPDC, you don't need to do partial trace, you can do a full trace. So you can kind of measure the mode, signal mode directly, and you can show that it can lead to squeezing. Of course, you need to put in a cavity and so on and so forth. So here what they do is that they use this amplitude squeeze state as their probe, okay? They do the homodining as well, like what Wu proposed, and that gives you access to very important parameters, space. And what they have done is, this is measuring from signal analyzer, they are able to reduce sort of the noise floor of the measurement. This is the short noise limit, and they can go beyond the short noise. So they can go at relatively low powers. A caveat there is that they are able to improve the signal to noise ratio by only 13%, by a lot of work. So there is still a lot of scope. It's not that we have improved the signal to noise ratio by orders of magnitude yet. There is still a lot of scope and a lot of room to kind of improve. After this paper came out, there's another paper that appeared in Optica in 2022, where they did quantum enhanced Brillouin scattering. Like Raman scattering, you also have Brillouin scattering, which is kind of process-wise not that indifferent. In this case, they also do imaging with squeeze states, and you can kind of see they have some I think fused silica, if I remember correctly. They do Brillouin scattering from that, and you can kind of see the signal to noise ratio with squeeze states, which is much better than what is achieved with coherent source. So using of squeeze states is something which is being explored. And the important thing is you can generate squeeze states using nonlinear optics, either to SPDC, that's two mode squeeze states, or OPA, where you have one mode squeeze state. So that's something that we need to think about. Now, the thing also that we need as spectroscopy community to start thinking about is not just measuring the intensity of the electromagnetic field or amplitude and phase of the electromagnetic field, to effectively embrace photon detection, photon number distributions, and that's what is most relevant. Okay, so with that, we'll take a little break now, because now next we'll go into emerging perspectives in quantum spectroscopy. Of course, this is not going to be too long, but I'm going to talk about three things: use of Hongo-Mandel interference, use of quantum process tomography, and use of joint spectral amplitude. Three important quantum observables that can be used to probe materials. Okay.